Welcome to the fourth part of the chapter Gravitation. In this particular section, we are going to talk about the Earth's gravitational acceleration. As we know by the Newton's second law of motion, a force acting on a body is resulting in the acceleration of that particular object, and the formula for that already we studied, that is the F is equal to ma. It means that if a particular object is having a mass m and the force F is acting on it, then it will start to move with the acceleration a. And this is called the acceleration due to gravity. This is called as the acceleration due to gravity and is denoted by the small letter g. And the gravitational acceleration due to gravity is nothing but the vector quantity which is having a magnitude as well as the direction. Now the next part what we have to study, that is the value of g on the surface of the earth. What is the value that we will see with the some derivation part. In that, the first of all, that is the F is equal to capital G, capital M, small m upon r square. Capital G, that is the universal gravitational constant. Capital M, that is the mass of the earth, and small m is the mass of the object, and r is nothing but the distance. Another formula that is already we have studied, that is the F is equal to ma, and a can be written as g, the gravitational acceleration, and that's why we have F is equal to mg. Now after that we can go towards the comparison of both the equations, that is the equation number 3 and equation number 4, and we are getting over here with that is the small g is equal to capital G, capital M upon r square. And when we will substitute the standard values for the g, capital M and the r, we are getting on calculation, that is the 9.77 meter per second square. This is nothing but what the value of g for the earth. This is the average calculations we are having, which gives the value for the g. Now when we talk about the g, there is a different factors which affects the value of g. If we are thinking that the value of g is a constant throughout the earth's surface, then it's not the case. With a change in a different factors, the value of g changes or at a different places on the earth. First of all, in that the first part is change along the surface of the earth. As we know, the shape of the earth is not the exact spherical. It's a bulging out from the equator. If I want to draw this picture for the earth, and this is the axis of rotation, then you can observe these two places. It's a equator. This is called as a equator, and it's a bulging out. It's flattened from the poles, from the top north pole and the south pole. It's a flattened, and that's why this distance is more as compared to this value. If I am labeling this as a r1 and this as a r2, then r1 is greater than r2. So this is what we have, the shape of the earth, and due to that what happen, if the value of radius is increasing, the value of g is different. G is the highest, this at the poles, and 9.78 at the equator, means the lowest value of it. There is a difference because the poles are having a lesser radius as compared to the equator, and if you will see in the formula, there is a r in the denominator, means if the value of r reduces just like the poles, then the value of g will be higher. Now the further part, the next part or the next factor which affects the value of g, that is the change in height. Change in a height is also the similar case. If the height is increasing, then the value of g will reduce, because height is increasing means the distance between the center and the object will increase, and due to that there will be a reduction in the value of g. You can see over here the first one, that is the surface of the earth, is the average value, that is 9.8 we are taking. Then Mount Everest, which is almost 8.8 kilometer, is having a height, then the value is almost 9.8, because 8.8 kilometer is nothing if we will compare it with the radius of Earth. In same way, the other factors they have given, see the last one, that is the height of communication satellite, which is almost at a 35,700, and the value is a 0.225. You can observe over here, as the height is increasing, the value of G is decreasing. This shows what, as we are moving away from the Earth's surface, the force by which Earth is attracting will go on reducing. Means indirectly, the gravitational acceleration due to gravity of Earth will reduce. The third part what we have, or the third factor which affects the gravity of the Earth, that is the change with depth. Means if we are going inside the Earth's crust, then what is expected? This is expected that the gravity will go on increasing, but it's not the case. Why it's not the case? Because suppose if we are going inside the Earth at a certain depth, then at this particular point only this is the portion of Earth will be considered. Means the mass of Earth is also reducing as when we are going inside the Earth crust, because only this much portion of the Earth will be considered, and that's why the combined if result of it, or the combined effect of this R and M, is nothing but deciding the value of G, and that gives a decrease in the value of G as we are going inside the Earth crust. The next part what we have to study, that is the mass and weight. Mass is the amount of matter present in the object. Mass is the amount of matter present in the object, and the SI unit of mass is kg, and it is a scalar quantity. It's the mass don't have any direction, it's having a magnitude, and that's why it is a scalar quantity. Whereas when we talk about the weight, weight is defined as the force with which the Earth attracts the object, and F is equal to mg is a formula for the weight. We can write weight is also the force by which Earth is attracting any particular object, and that is the mg. This is derived from mass into acceleration. Further part is, the next what we have to study is some numericals they have given, which you can go through, and this later on we can discuss. The next part we will discuss about the gravitational waves and some more topic after this.